of Education. And my name is Sheng Wang, and my advisor is Professor Wang. And this is my report. My topic is study of the rectified vortex motion in a race of equal size of naive films. Let's talk about a special phenomenon in superconductor. So this is my outline. At first, I will introduce some background of superconductor, and then I will perform some better review about the pinning size. And what is pinning size? I will talk about what is pinning size better. And then I will review some better about the asymmetry pinning size. And then next part is my verification and measurement technique. And next, result and discussion. Final is my summary. So let's start. First, I will introduce the background of superconductor. So there are two properties of superconductor. The one is zero resistance, and the other one is maximum effect. And the maximum effect, in other words, means perfect diamagnetic. And it means if we apply a magnetic field to the superconductor, they won't eat into the superconductor. And then there are two types of superconductor, type 1 and type 2 superconductor. And what we prefer now is type 2 superconductor. So in our section, we are focused, in our section, the type 2 superconductor has three states. The first is maximum state, and then it's mixed state, and then it's normal state. And what we focus on is mixed state. So we can see in mixed state there are special phenomena. If we this is a top view on the superconductor in mixed state. So if we apply a magnetic field to this superconductor, the magnetic field will into the superconductor by the quantum line. So the point is the flux line. So, and we talk the flux line vortex. So then I will just talk vortex. I won't say flux line. So this is the superconductor in mixed state, and we apply the magnetic field perpendicular on the superconductor. So the pink circle is the vortex. So if we inject a current to the superconductor in the x-axis, the vortex will tend to move easily because of the Lorentz force. And we know that from this equation, and we know that the vortex moves. So the vortex will get the velocity. So the velocity of the vortex will induce electronic field. So we can measure we can measure a voltage in the x-axis too. So and this is our major technique too. So but there are a very important thing. If the vortex moves, the energy dissipation will occur. So in our application, what we want is we want the high current density and low energy dissipation. In here, what we want is high current density, high critical current, and low energy dissipation. And we know that the energy dissipation is because of the velocity of the vortex. So what we got to do is we want to lower our velocity of vortex. So we can see here, we use the invariant technique to design the defects on the superconductor. And there are phenomena about the vortex will be pinning by the defects. That means the vortex won't move. The velocity of the vortex will be zero. So will be similar to zero. And this is called this defect to pinning the vortex, we call them pinning size. So then we will perform some paper reviews about the different pinning size. So there are many different pinning size, like a triangular array and a square array. And we can see from this image. This image is a triangular array superconductor on our beam. So we can see here, they make this fabrication and measure and inject a current in this way in the x-axis and measure the voltage in the same way too. So this is their result, the RH loop in here. So we can see there are a very special phenomena in the spatial magnetic field. So in this magnetic field, we know that the resistance will be there are peak of the resistance. We can find it, and here we just say that the low resistance is mean the low velocity of vortex. So in here we can know that the vortex will be pinning by these defects. So this magnetic field, this magnetic field, we call them magnetic field, and this effect, we call them pinning effect. Okay, so that's the background of the pinning size, and we can see here the paper is almost the full paper. So if I am missing, I will say that's not fish. So now we have to perform some new paper, new ways about the pinning size. And here is a special pinning size about the symmetry pinning size. So we can see here, it's a science paper in 2003. If we make a triangle pattern on a square array, and we can see if the vortex moves in this x-axis, the energy of the vortex will be the symmetry. You can see from here. If the vortex is in here, and the velocity of the vortex move to the right way and move to the left way will be the same. So if now we inject AC current, so AC current is mean the vortex will move to the right way and move to the left way. So we will measure a same velocity of the vortex. So the voltage we measure will be the 0. It's in an x-axis. But if the vortex moves to the y-axis, we can see from here, the potential, the energy isn't symmetry, it's a symmetry potential. So the vortex will tend to move to the right, tend to move to the left way and hard to move to the right way. So the velocity of the vortex will be different. So it means the velocity of the vortex move to the right way is more higher than to move to the other way. So we will measure a peak of the voltage in here. So we will measure different voltage if we inject a current in axis or a current in the y-axis. And this effect we call them rectified effect. So we can know from this equation. So now if we solve so now we can know that the fabrication like this, the pattern like this, the y-axis will have a symmetry potential, but x-axis will have a symmetry potential. But in our pattern, our pattern is a simple pattern in a triangular array. So the potential in the x-axis and y-axis is both the same potential. So it's a symmetry potential, and we want to make some difference to that the y-axis will get a symmetry potential. So we make a pattern like this. It's still a triangular array, but it will be the symmetry potential in the x-axis because the interval between the vortex in x-axis will be the same. But it's a symmetry potential in the y-axis because the interval between the vortex in the y-axis will be different. And we can know that because the interval different, so we'll get a different density from high distance to low from this figure. And we can know the interval axis will be the set and y-axis will be the defect. So this is our fabrication process. We use the EV writing technique to write our pattern and use the RIE to etch our substrate. And finally, deposit it. Now we use the sparkle. So then this is our final fabrication. That is constant increase from the 390 nanometer to 408 nanometer, and which increase start from the top line to the bottom line. So here is the high density, here is the low density, and the diameter is 250 nanometer. And then we use the spring to do the 4-part measurement. And here is our curve about here's our result of our data. And we inject a current in the x-axis and we measure the voltage in the x-axis too. So the red point is we inject a positive current, and the green point is we inject a negative current. And this is the RH loop, and we can see here the resistance of between the axis, between the red point and the green point is almost the same, except in here. Here is our measured field. So we can see here, the resistance of the green point, negative current, is higher than positive current. So we do the IV curve so we measure the IV curve in this measured field and other field to see that. So this is our IV curve of the measured field 145 OE and the other field 120 OE. And we can see that if we are not in the measured field, the voltage we measure will be the same. But if we are in the measured field, there are a little difference between the positive current and negative current. So now we can see here, if we inject a positive current, the vortex will move to this way. And if we inject a negative current, the vortex will move to this way, from low density to high density. So we can know from this equation, the voltage will depend on the velocity of vortex. So the red point is more higher than the green point. This means the velocity of vortex is more faster than the green point. So we can see here, the vortex will tend to move from the high density to the low density. This is our small result. And we try to explain why is that. If here is a regular triangular array, and the vortex interaction will be the same between the vortex and its neighbor. But this is the space gradient array. It's our fabrication. The vortex, the interaction between the vortex and vortex in the x-axis will be the same, but in the y-axis won't be the same. It's more large in the top and more small in the bottom. So the vortex will tend to move from the top to the bottom, and from the high density to the low density. So we can get a summary in our. We can get some summary from that. The first is we can see that the resistance measurement. We can found some different. We can find some difference between the positive and negative DC applied current only in the measured field. In other field, you will find the phenomena. And the other summary is the vortex will tend to move from the high density to the low density. So we can use this phenomena to prepare to do a fabrication, to do a measurement like the pattern we just reviewed. In the y-axis is asymmetry and the x-axis is symmetry. Yeah, and this is what I have done now. And in the future, I will measure in the AC current to see this deep curve. Yeah. And this is my report. Thank you for your attention.
就是你有时刻一些 artificial 的 pinning size， 对不对？就是说，假设你的洞本来是10颗的深度是100纳米，那你再盖2毫米上去嘛。那如果你10颗是200纳米的深，再盖2毫米上去，随便啦。
OK， 那深度呢？深度，那个就是我们一起的深度跟我们的 pinning size 的，就是跟我们的电能力量的话，只要我们的电深度大于一个高度的话，大于一个深度的话，那我们各种的 vortex 的电能力量就不会有太大的差别。就是说，我们只要有动就可以了。那动的话不要太小，只要大于60纳米的话，那再大再小，它的pinning的低位不会差。
还有其他同学问题吗？就是我想请问一下，就是说，因为你是做乖轴，它是不对称的，那它不对称的距离会影响它整个效果。因为我看你那个 EP 写出来的那个，就是看起来就是很对称啊，可是所以我在请问它的大小，它是不对称的大小，然后还有它的大小会影响就是说你实验的那个结果。
这个的话，就是其实，因为我们现在的话，它做的间距的话，我们现在做的间距只有就是0.22 nanometer， 所以它的很小。那它的效益的话，我们看到的话还是有的，就是我们刚刚讲到还是有的。但是我们原本预期的差蛮多的，就是它的 peak 产生的空度其实不高，所以我们未来的话会预计就是想要做一个。所以未来的话，我们会想要，就是因为它其实如果说间距很大的话，它会观察到一个就是负向电有负向电压跟正向电压，而且它的值都还蛮大的，所以我们未来的话会去做一个比较大的变化，因为我们这边的话每个间距只有0.22，那我们观察到的数据都很小。那我们未来的话会做间距有到1 nano 的，那这样子的话，我们预期观察出来的效果会比较明显。谢谢。
好，那我们就谢谢王胜豪同学。